Good evening, everyone. Myself, Bhargava Hanumanth Patil, Department of Physics, Alva Institute of Engineering and Technology, Moodbidri, which is affiliated to Vishwasya Technical Institute, Belgavi. I am pursuing my PhD under the guidance of Dr. Shashi Kumar K of same department. My topic will be on the experimental proton and carbon solid state NMR signal assignment using DFT calculations of paramagnetic copper to pyrazine carboxylate complex. The outline of my presentation will be the introduction part, in which I am talking about the interactions and techniques involved in the NMR and the solid state NMR, and the application, some of the accomplishments in the field of the NMR and the solid state NMR. The NMR of paramagnetic system will be having some challenges and the developments in the field of this paramagnetic system has been discussed here. The results and discussion part is applied, studied the one-dimensional 1H, and we acquired the spectra from using one-dimensional 1H and 13C2 depth experiment. The DFT calculations on the complex is done by geometry optimization and followed by the frequency calculations. Then we assigned the signals using context shift calculations. The location of the unpaired electron is found by the molecular analysis, and that's the conclusion part. The NMR fundamentals, which is having, since the NMR nuclear magnetic resonance, it mainly depends on the nucleus. When the non-zero spin nucleus is placed in the non-zero magnetic field, two energy fields are split each other, and when the RF frequency irradiated to this, and they combine each other and give a NMR signal. This NMR signal resembles the spectral signature of the chemical group present in the molecule. In the scene, as in scene of ethanol, the three signals, which is resembles the CH3, CH2, and OH group, and hence the chemists which use the NMR chemical shift table to calculate their work. There are some techniques which is involved in the solid state NMR will be the magic angle spinning. When the sample is spun at a particular angle, the spatial averaging of the widespread signals will be removed and the narrower signal will be get. And then another is cross polarization signal, in which the signal, the insensitive nucleus is enhanced by the polarization transfer technique, and heteronuclear decoupling, in which we eliminate the coupling between the nucleus and the reducing the language, and these things bring back by using the recoupling techniques. And some of the applications of the ssNMR will be the as shown in the figure. The one is the monitoring drug trafficking, the neurodegenerative disease study, in situ metabolism in organism, and in situ and ex situ study on alkyl battery, and the NMR on food produce. Among all the interactions, the hyperfine interactions will be the most prominent in the NMR of solids. But in the case of the liquid, the chemical shift, the dipolar, the J coupling, and the hyperfine is well exploited in that region. But in the case of solid, the hyperfine interaction will be less explored. So what is this hyperfine interaction? The hyperfine interactions is nothing but the interaction between the nucleus and the unpaired electrons. If there are the close relations, the Fermi contact interaction will be the prominent. If they are a little bit away from each other, the pseudo contact will be the to interact to pseudo contact interactions. The unpaired electron, which is a characteristics of the spin density, which give a rise to the Fermi contact interaction, and which is dominant in the small paramagnetic metal complexes, and the pseudo contact is relatively weak, which is averaged by the magic angle spin. Some of the challenges in the field of solid state NMR will be this Fermi contact interaction deviates away from deviate away from the normal chemical shift range, which makes the signal assignment will be difficult, as is seen in the case of the cyclone, which is diamagnetic. Here we get the three signals, which is assigned easily. But when we put the copper in that diamagnetic system, it becomes paramagnetic complex. which makes we get the three signals which is out of the range, and it makes us the assignment will be difficult. By this, the conventional NMR techniques will be not applicable due to the fast relaxation, which is relatively weak proton-proton dipolar network, and loss of the sensitivity resolution due to the broadening due to the fast relaxation. The Ishi and co-workers in 2003 spin the sample at more than 30 kilohertz to enhance the sensitivity of the one proton and the carbon signals drastically. So the simple Hahn echo experiment will be efficient for signal assignment, and the fast reaction makes the interscan delay short. Fast operation makes the signal to noise ratio better, and the large Fermi contact shifts improve the resolution furthermore. And this all the developments which is applied by the Kumar, Swamy and co-workers to the copper cyclan complex, and by using the 2D dipolar inept and the DFT category, they assigned the signals successfully. These things, these developments are applied to our complex, and then the pyrazine 2 carboxylate is a ligand. Due to its lone pair on the nitrogen, it coordinates with the metal more prominently. And since it is a potent antibiotic due to high lithosity, so, most probably in the treatment of tuberculosis is used. There are two spectra which is given, which is well studied, because the diamagnetic shifts, proton diamond shift will be between the 0 to 14 ppm, and the carbon shift will be between the 0 to 220 ppm. And when we put the paramagnetic copper in the pyrazine 2 carboxylate, becomes the paramagnetic complex, which has wide application in the many areas like reactive center in the anti-tumor, in the field of zeolite supercage, and field of nanochannels, metal organic frameworks, and mixed metal molecular magnets. The sample is took in the 1.3 mm rotor, and we put it to the probe, and then we put into the magnet, and when the sample is spin more than 50 kilohertz, the signals will be enhanced drastically, and the pulse sequence is applied of 90, 180 and 180 signals are applied, and due to the depth sequence we acquired a signal, three signals, which is gone out of the 0 to 14 ppm, which in case of diamagnetic, as we seen here, which is out of the range. And then in the case of we get 4 out of 5 signals we get, in which those are out of the 0 to 220 ppm. It shows that 1H and 13C signals are unassignable. Since the assignment, the DFT calculation is the key to assign these signals, since the spin density or characteristics of the unpaired electrons, the DFT calculation has to be done. To do first, the geometry optimization has been done. The initial structure is taken from the claim co-workers. When we give through the Gaussian software, the optimization has been done using the UB36311G plus D basis set. We got the optimized structure, which is having the CUN bond will be in relation with the experimental data. So, and all the CUN and CU distances are most crucial in understanding the spin lattice, which is also in the close relation with the experimental data. So once the optimization is done, the frequency analysis has to be done. We are given the frequency calculation under the UB36011G plus D basis set. We acquired the IR spectrum, which is having no negative frequency, since we can tell that the spectra at which the global minima has been reached. And this vibration analysis has been performed using IR data, has been get from the Lewandowski and co-workers work. These vibrations are in relation with the experimental assignments made by the Lewandowski and the co-workers. The DFT since the 6311G plus D basis set and experimental will be close relation to each other, hence we can say that the 6311G plus D will be the accurate DFT structure. Hence, these are the prominent vibrations which we get from the Levendos in the experimental vibrations. Once the once the frequency calculation is done, the signal has been assigned from using the density functional theory. The spin densities has put into the equation, and we got the theoretical and the experimental shifts, out of which the 4 signals has been identified and one signal is not identified due to the loss of coherence between the copper and the carbon, which is close to each other. And in the same way, the proton shift has been which is in the close relationship with each other. And the assignment, hence the 13C and the proton signal assignment is completed. Hence, then the molecular orbital analysis has been done using the giving the command pop which is equals to full. Hence, we get the from the crystal field theory, the lone pair electron will be in the square pair, and because of lone free unpaired electron will be in the dx square minus y square orbital. For our calculations, the location of unpaired electron in the paramagnetic CU pair will be dx square minus y square orbital. Since the conclusion of our work will be the very first magnetic approach, more than 50 kilohertz is essential for one-dimensional proton and 13C depth spectra of paramagnetic copper pyroxene coppers. Hence, the DFT calculation vibration analysis will be crucial for the validation of the structure. Once the validation is done, the spin densities from the DFT calculation, we can assign the proton and carbon signal be assigned. Hence, there is no need for the two-dimensional correlation will be minimized, and the location of the unpaired electron will be acquired from the molecular orbital analysis. And I have been thankful for the cluster domain Lemon France for calculations, and I thank you all the other co-workers who helped me in doing this work. Thank you.